Hi, you are at level 9 out of 30 easy steps to understand everything about Einstein's special relativity. My name is Tom, and in this level we will meet Hans Christian Ørsted. In 1820 he unlocked a major secret in science and in physics. You want to know what it is? Stay tuned. GP, hit it! Hans Christian Ørsted. He was here he is. He was not ranked among the greatest scientists and mathematicians like the other rock stars on Einstein's mountain in other levels. But still, he unveiled he exposed, he unlocked a major secret in physics. He was the first who witnessed during experiments that electricity and magnetism are connected and not two separate things. So there we go. He was the first. It happened in 1820, April. He was playing with a compass. It was near an electric wire which was running a current, and he saw that the needle of the compass changed when he moved the compass around this wire. Let's see it in animation. So here we have a wire on the left and we have a compass. And now we have a current. Let's start the current, which is nothing more than electrons running freely through the wires. Here they are, blue electrons. And when we move the compass near the wire, you will see that the needle changes its direction. In this case, the compass is a little bit below the wire. And this is it. There has to be something mysterious in the air created by this wire, which has a running current, that affects the needle of the compass. And this was a major breakthrough in physics. So here we see it again. And I did some more things. Forget about the green stuff. I will talk about this later. So we again have the wire with the running electrons. And somehow physicists decided if the electrons go from right to left, the current goes from left to right. Why? Maybe it's because electrons have a negative charge, but to me that's really silly. But you know, that's me. I'm not a scientist. So, and we can express currents. I got this from feedback on level 6, Coulomb. Someone asked me, Tom, you have to explain what a current is. Well, it's electrons running freely through the wire. And the more there they are and the faster they move, the stronger the current. And the unit of measurement of current is ampere. And the symbol we use for current is the I. And what is 1 ampere? 1 ampere is the same as an incredible number of electrons passing by each second. So you're at the side of the wire, you start counting the electrons each second, and if you hit this number, which is on the screen, then you know, it's 1 ampere. So that's what it is. And then Ørsted started to experiment, changing the current, etc., changing the needle, and he discovered the following. He said there has to be something called a magnetic field in the air affecting the needle of the compass when the current runs through the wire. And he also tried to determine the direction and the strength of this magnetic field. And he said, well, it's circular, it's curly, it curls around the wire. And it curls in a particular way. It's perpendicular to the wire. And I drew 3 sets here of B. B is B is the symbol for the magnetic field. Like E is the symbol for the electric field. B is the symbol for the magnetic field. And it's everywhere, right? I just drew it here at three sets, but it's everywhere. He noticed that if you change the direction of the current, then the field lines of the magnetic field reverse as well. So they are still circular, perpendicular, but they go the other way around. He also saw that if you crank up the strength of the current, the magnetic field also increases, and it's proportional. So if you double the number of electrons, or you double the speed of the number of electrons each that pass by, then you double the strength of the magnetic field lines, and that's what you see. What we also see is that if you move away from the wire, the effect decreases. So the needle is not affected that much anymore. As soon as you go away from the wire, the strength of the magnetic field drops, which makes, I think, a little bit sense. It would be strange if that would be a constant magnetic field throughout the entire universe, right? And this is how mathematicians write it down. If this is your first level, you will now maybe feel like panic mode and maybe want to stop, but don't. I mean, we in level number 7, we talked about the secret symbol nabla. We also talked about the cross product. In level 2, we talked about vector fields. And if you master those levels, then this equation is not hard at all. It says the curl of the magnetic field, which is the nabla cross product B, it's just a curl. How curly is it? Well, that depends on some constant, in this case the magnetic constant, and the current. Well, in this case they used current density. But there's an easy relationship between current and current density, because current density is nothing more than the current divided by the cross-section of the wire, the surface area of the wire, if you cut it. So it's not the number of electrons passing by each second, but it's the number of electrons passing by each second per square meter of wire cross-section stuff. It's a little bit like flux. And in level 8, when we talked about Gauss, we did many animations on flux and what flux is. So if you are interested, you can go there to learn a little bit more. But this is it. This is the whole level. Congratulations. You are good to go to the next level. Okay. Yeah. I put a red square. This is it. So it's decision time. You can either now say, thank you, Tom, I'm moving up because I'm in a hurry. That's okay. You have the concept down. But if you are curious, brave, perseverance, and you want to know more, stay tuned for a little bit more details on this stuff. So here we go. Magnetic fields. I like to put stuff on the timeline because it gives me perspective, and it also tells me how many steps were needed to discover certain things and how much time was in between there. So way back, the Chinese already invented the compass. And one of the famous, this is not Chinese, but in 1269, Marie Curie did the iron needle experiment, and that's when people started to learn about magnetism more. It was special because Aristotle, who we will meet in future levels, he was not the experimental guy as Marie Curie. So he broke with the time spirit and did experiments. And that's how he discovered, a little bit about what the magnetic field looks like. Then we have Colchester, which discovered that the Earth itself is a magnet. He wrote a book called The Magnet. Well, it has a long name. And let me see in my notes. He experimented and he saw that the magnetic the needle of a compass was always pointing to the north on Earth. So maybe Earth itself is a magnet. And yes, it is. Our planet is a very big magnet. Here you see it. And it's the North Pole is the magnetic South Pole. Just, jokes from physicists to get you confused, right? Then, Michel. He saw that if you have two magnets, that the north poles, they will repel, south and north, they will attract, and he did some experiments to understand how big is that force. And he saw that if you move the magnets away from each other, then the force drops by the square of the distance. It's exactly like Coulomb, the electrostatic force in level 6. That force also drops by the square of the distance, and it's nothing different for the magnetic field strength. There it is. So, level 6. Yeah. So, level 6 is the level about electricity. All the other stuff was magnet stuff. But Coulomb also did stuff on magnets. He tried to cut a magnet in two to see if he would end up with a north pole or a south pole, just as we have positive and negative charges. And what do you know? We can't. Whenever you cut a magnet in two, you end up with two new magnets, no matter how long you keep doing this. So apparently nature has decided that north and south poles always come together. Then electricity, Gauss, it was the most biggest level of all up until now. Level 8, he discovered all kinds of stuff on electric flux and how to look through walls. So if you want to know more, go to level 8. This is the level where we are. So we had a big jump, about, no, it's a little jump. It's about 7 years later. Others start doing experiments. Ampère is a really famous name, of course, when it comes to electricity. I'm going to skip a few, just giving you the overview. And then, in the next level, the level after this one, we will talk about Michael Faraday and the law of induction. And there you truly see the marriage between electricity and magnetism. Skip this. We will talk in level 11, which is like the summary of the all 10 previous levels. Will be summarized, and we add a little bit stuff extra in level 11, which is Maxwell's equations. But I'm getting ahead of myself. So this is where we are now. We are now in 1820, and it will take another 85 years to get on top of Einstein's mountain and get to his special theory of relativity. So this is an overview on the timeline. Let's talk a little bit more about magnetic fields itself. Here we see a beautiful picture. I think it's the magnetic field of the sun, which is not constant, it's fluctuating all over. It's a vector field, level 2, vector fields, remember. And sometimes they use the H for the magnetic field and sometimes the B. Why? I don't know. They are the same if you want to calculate them, with the exception of some constant. Well, good for the physicists, good for them. And naming conventions are all over the place. I mean, you have to be really careful when you dive into magnetism, because if you look at the H field, it has different names and different units of measurements. The same for the B field. And sometimes the same name is used for either the H or the B field. Sometimes they also talk about the flux, which is a little bit more like Gauss looks at electricity using the flux concept. So be careful. That's what I want to tell you. If you really want to solve real problems and do calculations, be very careful about what you are looking at and which unit of measurements are in place. Let's dig a little bit deeper on the math. So I already showed you this one. Electricity gives curly magnetic fields, but before 1861 it was written down like this, like a curve integral. Again, if you're new, level number 8 Gauss, we talked about curve integrals and surface integrals. I will have an animation, explain it to you in detail how this equation works. But what we see is, we see in the green the magnetic field B. We see in purple something called delta L. Well, I will explain it shortly. And we see the magnetic constant again. And we see the red I, which is the current. How does this work? Here it is. And unit of measurements, I mean, if you're a big fan, sometimes I like to look at units of measurement. There are many different ways to express a single Henry, you know. There they are. So again, the wire. And now I'm going, what I did just do. Tom, what did you do? I put a hypothetical yellow curve enclosing the electric wire. And just as I did with Gauss, where we talked about hypothetical volumes, this is a hypothetical curve. But the hypothetical surface, I choose a very weird looking bird cage. And I told you, physicists and mathematicians will be shocked because they will pick a perfect sphere or a perfect cube or cylinder. In this case, they will be shocked as well, you know, because they always will pick a perfect circle for the yellow curve. I did not do this. Let's spin it. It's just an imaginary, arbitrary yellow curve. And closing the wire. And now let's put the formula to practice. We are going to zoom in on the curve and we're gonna pick a little piece of that curve. Here it is. This is a little piece of the curve. And this is what delta L is in the equation. Delta L is the length of the yellow curve, the entire length. And delta L is just a way of mathematicians saying a little bit, a piece of the full length. There it is. And at that point in space, there will be a magnetic field, which is expressed by a vector. And the formula tells us that the dot product between the green magnetic field and delta L, in this case expressed as a vector as well, will give us a little bit of the current running through the wire. And if we do this, and this is what the secret symbol is, the curve integral or the line integral, that if you do this all across the yellow wire, the yellow curve, and you add them all up, you will get the magnetic constant multiplied by the current. So, and this is like Gauss. Gauss could look through walls. He could tell you what was inside a volume without ever going in. In this case, you can tell how much current is running in the wire without ever going to the wire. You are staying at a safe distance from the wire and you're taking the dot product between the measured magnetic field and a little bit length of the curve, and you do this all around and you add them all up, and voila, you know the current in the wire. It's really like magic, right? This stuff. So there you go. It spins. Of course it spins. I should have shown that before. Ready for another bonus. You can go to the next level, of course. But if you want to do a little bit more, we are going to apply the formula. We are going to do some rock climbing. We are going to calculate how strong a magnetic field is given the distance from a wire. Ready? There we go. We will repeat Ørsted rules because we need them. Here it is. The blue thing in the middle is the electric wire. We are facing it on the cross section. So the electrons are popping out of the screens into our eyes. And now I did not pick an imaginary, arbitrary yellow curve. No, I picked a green curve. And yes, I did what all the others do. I picked a perfect circle. There it is, and the diameter of the circle is r. And now we are going to apply the formula around the green curve. So here it is. I want to do this. For every little piece of the green curve, I want to take the dot product of the magnetic field and a little bit of the length of the green curve, and then add them all together to know what the current is in the blue electric wire. So, well, thanks to Ørsted, we know that, one step back, delta L will be a small piece of the wire. So it's, and we use it as a vector, so it goes around like this. So there it is. And if you remember level number 7, where we talked about curl and divergence, we also talked about the dot product between two vectors. And one way of calculating the dot product between two vectors is taking the length of vector 1 multiplied by the length of the second vector multiplied by the cosine of the angle between the two vectors. And we talked about trigonometry as well, sine and cosine, and I hope I made you feel relaxed about these things. You know, it's just a table inside your calculator. I think that's what I told you. Well, what is the cosine of, let me draw the, this is the wrong way around, but the magnetic field, the direction of it, according to Ørsted, is perpendicular. So it's always the same as delta L on every point on the curve. So the angle alpha is always 0. And what is the cosine of 0? It's 1. If you didn't know, you can just take your calculator. Cosine of 0 equals 1. So we can drop the cosine thing. So we simplified the formula a little bit. Ørsted also told us that the strength of the magnetic field only depends on the distance between the point of interest and the wire, in this case r. And on this green curve, it's always the same. So whatever the magnetic field strength will be, it will be a constant, which simplifies things, because if it's a constant, we can take it away from the line integral, the curve integral. So now it says, take a little piece of the green curve and add them all together, which is exactly the length of the circle. And I'm sure this is something, you know, what is the length of a circle with radius r? It's 2 times pi times r, which is something that I think most of us will know. So I can replace the whole complicated looking line integral with 2 pi r. Then bring them to the other side of the equation sign. Remember, I think level 3, when we talked about the basics of algebra, you can shovel things around. Here we shoveled. And now you know the strength of a magnetic field in the vicinity of a wire is the magnetic constant times the current in the wire divided by 2 pi r. And there you go. Congratulations. You now can do the magic. I want to thank you all for watching this level and hope to see you at the next one. GP, hit it!